Hello, my name is Madeline Jekot and I will be presenting on KI4. A brief overview of this presentation will go over concepts learned in electromagnetics, microelectronics, and systems and signals. From ECE 332, I will be discussing amplifiers. 312 will cover frequency shifting and the mixer, and then finally I will end with antennas, and that is 342. Now, all of these components I will be discussing in relation to the radio system block. The part I will be looking at is outlined in red, and I will start at one end and work through the other. To begin, I will look at the preamplifier. This is a differential amplifier and is normally made of MOSFETs. This is a 332 concept. As we know from KI number 2, we have a very low voice input signal, and so to drive the mixer and to get useful information out of it, we want to amplify it. We use a preamplifier to do this. So before the amplifier, we'll have a fairly low amplitude wave as seen on the slide, and then we'll move to the after preamplification, which just has a higher amplitude. The next piece I will talk about is the mixer. After the preamplification, we want to multiply the input signal, or the amplified signal, with a high frequency wave. This is because we want the antenna to have a higher frequency wave coming to it, so it can be smaller. And then, so we know that if you multiply two signals in the time domain, that this is just convolution in the frequency domain. Although because the high frequency cosine wave can be written as complex exponentials, we can now say that this is a frequency shift, and therefore it will just be, the new signal will be at high frequency. As you can see on the screen, the red wave is the amplified signal from the previous slide, and then you multiply it with a higher frequency, which will produce the blue wave. And so there is a black wave on there as well, but this is just a shifted cosine to further, or to show that when you multiply the two signals together, the higher frequency will follow the pattern of the low frequency wave, and so the low frequency creates the envelope for the high frequency wave. This is a great mix of our courses because in reality it's a MOSFET that multiplies these two signals with capacitors and resistors to get the signals together, and then it's a MOSFET to multiply them. And then 312 beautifully describes the math and the theory behind mixing the signals. Next, we're going to move on to the power amplifier. The reason we have this is to drive the antenna and match the impedance of the antenna, because we want a high gain and we want our signal to also be amplified in this. After we use the power amplifier, we'll move on to a bandpass filter. This is to help get rid of noise, and normally it cuts out the frequencies that are in or out of human hearing range for a phone, for example. Those just aren't important to us. This can be made out of a high-pass filter and a low-pass filter, although you want to make sure the poles of the high-pass filter happen first, or else you'd just be cutting out low frequencies and it wouldn't pass anything if you tried to make it in reverse. So you want a high-pass filter and you want your bandpass to be cut off using a low-pass filter. This will give you a range between about two frequencies, and can be seen on the slide in the graph. Ideally throughout a cell phone, there will be several bandpass filters and several power amplifiers, but for simplicity, I will only go through the concepts once for this presentation. Next, we're going to move on to the diplexer. This is the stage before the antenna. The main reason for this is so you don't create a walkie-talkie. in a walkie-talkie, you can only have one person or one signal going out at once. What a diplexer does is it has a low-pass filter and a high-pass filter and allows an incoming and outgoing signal at the same time. This is so you can like interrupt your friend on the phone or just have a normal conversation. The diplexer works though because the signals are set at different frequencies, and the company will design that and figure that out. So this also mixes several of our classes together. Finally, we will move on to the antenna. This is the key piece that sends and receives the signals. Now, as discussed previously, we want the antenna to be very small because you don't want to carry around a giant phone. And so we know that the size is proportional to the wavelength, and so you want it to have a fairly small wavelength. So in order to get a very small wavelength, you want a really high frequency, which is the exact purpose of our mixer. We shifted our signal up to a higher frequency, and so we know that our antenna can be smaller now. The most common antenna is an omni antenna. This is so your phone can receive a signal from almost anywhere. You wouldn't want your phone to just work in one position like the old TVs and some dish satellites work. That wouldn't make having a cell phone very easy. So the omni antenna tends to have a 360-degree radial pattern as seen on the slides. So as you can see, that if you break down a phone and you keep breaking down a phone and all the complexities it has, you can break down the topics into enough small pieces that have been covered in systems and signals, microelectronics, and electromagnetics. And these all work together to make something as useful as a cell phone work. Thank you so much for your time. Have a wonderful day.